Alrighty guys, we're going to go ahead and get started with multiple charges. In other words, advanced Coulombs Law. So first thing we want to talk about is that we're going to see some cases in which there are more than one charge acting on an object. So right now we've been doing some pretty easy problems where we just have two charges repelling or attracting each other, but now we're going to start having 3 and possibly 4. So for instance, here's our basic case where we have these two charges, but now we have this charge in between the two. And we're going to say that this positive P just denotes a positive test charge. So when we're given a problem like this, we need to consider how much each force is pushing or pulling on the object, and then determine the net force. And the reason we need the net force is because we have multiple forces at work here. So let's explore this with just 2 charges at a time. And again, that positive P just means that it's a positive charge. So I'm going to go ahead and get rid of my right charge, and now I just have my -1 Coulomb and my positive charge P. Well, first thing I need to think about is what direction is that positive test charge P going to feel a force? It's going to feel a force towards that negative charge because they're attracted to each other. Next, let's go ahead and look at the negative charge on the right-hand side. Well, positive P is still positive, so this time it's going to feel a force to the right. And again, that's because it's attracted to that negative charge. We're going to notice that the force that it feels from the -2 Coulomb charge is actually bigger than the force from the -1 Coulomb charge. And that's because we know that -2 coulombs is bigger than -1 coulombs in terms of charge. We want to make sure that we're denoting that with our arrows because we remember that forces are vectors and that the size of that arrow tells us the magnitude of the force. So the bigger the arrow, the more magnitude it has. And then the direction just tells us the direction the force points in. Now that we know what the force looks like from the -2 coulombs and the force looks like from the -1 coulomb, we can determine the net force here. And the net force is just us adding these up. So if we do that, we're going to find out that our net force is going to point to the right, towards that -2 Coulomb charge. Now let's take a look at a few other examples here. In each box below, there are pairs of electrical charges in 3 different arrangements. We want to draw a vector at point P to indicate the direction of the force that would be experienced by a positive test charge placed at that location. We also want to rank the magnitude of the forces from smallest to largest. So let's get started with the first one. On the first one here, I know that this positive test charge P is going to feel a force to the left towards that -1 Coulomb charge. But I also have -1 to the right, so that means that I'm going to feel a force to the right. So now let's take a look at letter B. Well, letter B, our positive test charge is all the way to the right here. So if we're thinking about the forces that our positive test charge is going to feel, the first force is going to be to the left in regards to our -1 charge right here. And then the next force we're going to feel is to the right. You're going to notice that this force, or this force arrow, is smaller than this force arrow over here. Why might it be smaller? Well, let's take a look. This +1 charge and this test charge here are very far away. Because they're far away, that means that the force that's going to be felt by this positive test charge is going to be a lot smaller. We take a look at C, we see that we have a positive force pushing it to the left, and that's coming from this +1 charge over here. Now we have this -1 charge, and this -1 charge is pulling it to the left as well. Because this is a positive charge, we know that negatives and positives attract, so in this case we have 2 arrows pointed in the same direction. Now that we've figured out all the component forces from each of our charged objects, let's go ahead and figure out what the net force is. Well, in this case we have 1 to the left and 1 to the right, so those are just going to cancel each other out, and our net force for our first example is just 0 newtons. Now for our second example, what does our net force look like? We have a big force to the left and a small force to the right. That means that our net force is going to point to the left. Lastly, we have 2 forces pointing to the left. We're going to just add those together because they're in the same direction and get a giant mega force pointing to the left. Let's take a look at our examples down below. This time we have more than just one charge. We have +2 here and -1 here. So if we look at this, our +2 is going to exert a force to the right. And how do I know it's to the right? Because this test charge is positive, and this plus 2 is positive, so it's going to push it to the right because it's repelling. This -1 is going to attract it to the right, so it should have a -1 force pointing to the right as well. I noticed that this force is smaller than my +2 force, and the reason why is that there's only -1 charge. This one had +2 charge, so less charge means smaller force. Now let's take a look at B. For B, we have a force pulling it to the left, and that's coming from our -1 over here. And now over here, we notice that we have +2. Well, it's plus, so it's going to push it to the right, but is it going to be the same size, bigger, or smaller? Well, it is more charged, so maybe it's bigger. But wait, if we look at this, we see that it's really far away from that. So because it's so far away, and because we know Coulombs Law, which is F equals K times Q1 times Q2 divided by R squared, we know that R impacts the force a lot more than charge does. Therefore, we're going to have a force that points to the right, and it's going to be smaller than our force that points to the left. Even though we have more charge here, it's because our charge is very far away. All right, let's take a look at letter C now. So letter C, we have +2 here and our positive test charge. That means that we're going to have a big force pointed to the right. I know it's big because I now have +2 charge. How do I know it's pointing to the right? Because it's a positive charge and a positive test charge, so they're going to repel each other. Boom. Now I look at my -1 over here. Negative means that it's going to attract this positive test charge, except the thing I need to note is that because it's so far away, even though it's attracting it, it's going to be a small force. Now let's do what we did before and figure out what the net force is. So for our first one, we got 2 forces that point to the right. We just add those on top of each other and get a mega force that points to the right. For letter B, we have 1 force points to the left, 1 to the right. The bigger points to the left, so our net force points to the left. Letter C, the bigger force points to the right, so our net force points to the right. But when you guys are doing problems like these, I highly recommend that you do them exactly how I did them. You break down the problem so that you have 1 force pointing to the left, 1 force pointing to the right, and then you figure out your net force from there. It will make things a lot easier. Now we're going to take a look at one of our last examples here, and this one's going to involve some math. So on the top, we have Q1, Q2, and Q3. So let's first start by looking at what forces are being applied to Q1 just by Q2. So let's ignore Q3 for a sec. Well, Q1 is negative and Q2 is positive, meaning that Q1 will be attracted to the right by Q2. But if we look at Q2, well, Q2 is attracted to the left by Q1. So what does that mean? That means that both of these forces here, Q1, Q2, and Q1, Q2, are the same. It's just that one points to the right and one points to the left, dependent on when we're describing it. Now let's find the other pair of forces in terms of Q1 and Q3. So Q1 is still negative, Q3 is positive. That means that Q1 is going to feel a rightward force towards Q3, and Q3 is going to feel a leftward force towards Q1. Now we just have one last pair to figure out, and that's Q2 and Q3. Q2 is positive, Q3 is positive. That means that these two things are going to repel each other. So Q2 is going to feel a leftward force, and Q3 is going to feel a rightward force. Now that we've assigned all the forces that these objects are feeling by one another, we can start diving into this question. Let's go ahead and calculate the magnitude of the force with Coulombs Law. We know that Coulombs Law is F equals K times Q1 times Q2 divided by R squared. So for our first force, which is F Q1 Q2, we know that K is 9 times 10 to the 9th. Q1 in this case is -4. And then this U right here just means microcoulombs, which is just e to the -6, times Q2, which is 8e -6. Again, it's microcoulombs. Divided by our distance squared. The distance between these two is 0.4 meters. Go ahead and solve, and we get 1.8 newtons. Now we're going to take a look at the force exerted by Q2 and Q3 onto each other. So we know that K is still 9e9. We know that Q2 is 8e to the -6, and we know that Q3 is 7e to the -6. The distance between these two we can see right here is just 0.2 meters, and we plug that into our equation and square it. Go ahead and solve, and we find out that that force should be 12.6 newtons. Real quick before I go on, some of you might be saying, but Mr. Weiss, shouldn't this have been negative? Shouldn't I have put -4 here? Keep in mind, I said that we're solving for the magnitude of the force. So magnitude is always the positive or the absolute value of this. All right, so now let's take a look at F, Q1, and Q3. So over here, we're going to notice that K is still 99. Q1 is still 4e to the -6. And again, it's positive because we're only concerned with the magnitude here. And Q3 is 7e -6. The distance, though, is going to be the distance from Q1 to Q3, which means that it's 0.4 plus 0.2, which gives us 0.6. We solve and we find out that our magnitude of the force should be 0.7 newtons. Now that we have all of these magnitudes, we can go ahead and add them up to find out the net force on each charge. So let's start with charge 1. We see that both of these forces point to the right, so we're just going to add these together. That's going to give us a net force of 2.5 newtons. Now let's look at Q2. Both of these forces point to the left, and we know in physics the left is considered negative, so we're going to subtract those two together. That's going to give us a net force of -14.4 newtons. Lastly, we have Q3, one force to the right, one force to the left. So the positive force is going to be FQ2, Q3, and the negative force is FQ1, Q3. Go ahead and add those together, and our net force should be 11.9 newtons. All right, so if we take a look at this problem here, this is our last one. It wants us to rank these in order from strongest to weakest. First thing I want to do is figure out what type of direction the forces that this positive test charge is feeling from these charges is going to point. So this is a positive test charge, so it's going to feel a force to the left by this charge and to the right by this charge, meaning that the net force felt here is just 0 newtons because it's being pulled to the left, pulled to the right, they're going to cancel each other out. Now let's take a look at this one. The negative is going to attract this to the left and it's close to it, so it's going to be pretty big. The positive is going to push it to the right, it's going to be kind of small. So this is going to feel a kind of small force to the left. Letter C, we have this negative that's going to pull it over to the left, and then this positive that's going to push it over to the left as well, meaning that this one's going to feel a huge force to the left. Letter D, positive, positive, so this positive is going to push it, and then this other positive is also going to push it. This positive is pretty far away though from this test charge, meaning that it's not going to be a lot of force that it's pushing it with. Still, two forces are going to point in the same direction, giving us a decently sized net force. Letter E, same exact thing, except now these two charges are negative, so we're going to be pulled to the left pretty heavily with this first one, and then the other one we're also going to be pulled to the left, but not as much because again it's pretty far away. Therefore, the net force here is going to look something like this. Letter F, we have two positives, so the positive on the left-hand side is going to push this positive charge to the right. The positive on the right-hand side is going to push this positive charge to the left. These forces are in opposite directions, so the net force here is just 0. Lastly, letter G, we have a positive here and positive here, meaning that's going to push it to the right, and then negative, and this is a positive charge. This positive test charge is going to be attracted to this negative charge, meaning that it's going to be pulled back to the left. It's not as big because we know that it's far away, therefore the net force here is going to kind of be a small arrow to the right. So if we're ranking these really quickly, strongest to weakest, well, the two weakest for sure are A and F because those are 0, so I can write that here. And then from there, let's take a look. Well, we know that these two point in the same direction for C, so that's going to be pretty strong. So C is by far the strongest. And then from there, like I said before, these two are in the same direction, these two are in the same direction, and these are in opposite directions. So B and G are going to be the same, but because they're in opposite directions, they're going to be kind of weak. And then D and E are going to be the same as well, because they both push in the same direction. So D pushes 2 to the right, E pushes 2 to the left. So D and E are the same as well. And the way I did this was just by splitting up into component form and then solving for the net force there. I needed to take into consideration the charge of these objects, but also the distance they were from the test charge.